Hello class. Today we're going to start the lesson 1 of electric circuitry. So this is something that you deal with every day, and our life pretty much depends on electricity and technology. So basically this powers everything that we use, and especially now during quarantine, everything is pretty much relying on electronics, including learning and teaching. So it's basically a lifeblood in our technology. It's kind of like, like blood courses through our veins and arteries. Electrons are flowing through the electrical conductors, giving power to the electronic device or appliances, kind of like our blood is giving power to the cells. Okay, so let's talk about some terms. What is an electromotive force or EMF? This is a misnomer. It's named really not the way it should have been, because it's not a force. So this is not a force. It is actually a potential difference. And a potential difference, you know this probably as more commonly as voltage. And one of the many sources of electrical energy is the battery. So we're going to be going over the sources of energy in more details later on. We call it AC or DC. So because you have a positive and negative charges on the battery terminal, you create an electric potential. So the key word here is a potential difference. So as you can see, you have to have a positive and a negative, and that will push the difference between the two charges, and it will create a potential or a pressure, and that will push the electrons to flow, and that will create the current. So what are the possible sources of the electromotive force? Well, we have an example is an electrochemical cell. So I'm going to call this the first one. And an electrochemical cell is where you have chemical energy being converted into electrical energy. So there are many different ways that we can get a voltage or electrochemical potential. We also can get voltage from a photoelectric cell. So a photoelectric cell, we all know this as the solar cell or the solar panel, and it converts light energy into electrical energy. The photoelectric cell or solar panel is very much like a green leaf. If you ever examine what a green leaf is, it is basically a photoelectric cell because it has chloroplast inside it. So it's kind of like a green leaf. I'm going to compare this with green leaf. The chloroplast within the green leaf is absorbing the sunlight, and it's converting the carbon dioxide that comes from the air and the water into glucose and oxygen. So it's a pretty amazing thing. So we got to thank plants for doing all that for us. And then we have a generator. So a generator, I'm going to call this number 3, is basically what it's doing is it's converting kinetic energy. So it has to be something that is moving. So it's converting kinetic energy into electrical energy. The generator does this through the principle of electromagnetic induction, and this actually is a unit all on its own. This will be a unit that we're going to be covering after the electric circuitry. After this unit, we're going to go over electromagnetic induction. That will then take us to the very last unit called the medical physics. Okay, and then we have the fourth type or the fourth source of electromotive force, a piezoelectric cell. and this converts mechanical pressure. So basically squeezing a crystal, so mechanical pressure, and it creates the potential difference. So it creates electrical energy. As you know, energy can never stay still, and it's always wanting to convert itself to something else. Then we have a thermocouple. Basically, it's an electric circuit containing wire of two different metal with two junctions placed at two different temperature. So a thermoelectric effect produces a potential difference and current when these two metals at different junction experience a temperature difference. So it has to have a heat flow. So this is heat energy converting uh, itself into electrical energy. So an example of a thermocouple would be a thermostat. So it is basically a bimetallic strip. Bimetallic meaning it is made of two different metals. So it could be something like this, where it has two different metals, and what happens is the sensor will then sense the change in temperature, and it will either bend up or bend down, and it will then trigger a switch, which will then either, if it's a thermostat, it will turn on either the heater or turn on the air conditioner. So that is how a thermostat works in your home or in our building. Now let's take a look at the concept of electric current. So what is an electric current? So you know that there is a source of the current, which is called potential difference or voltage. This is created between the terminals. So you have a positive terminal and a negative terminal, and between these two, you create a voltage. So that is the voltage between these two. Now, what happens is once a potential difference or voltage is created between the terminal, the electrons will flow. So there will be a free flow of electrons. So let's say this is the path, and the electrons are now free to flow. So the electrons are flowing, and they always flow in one direction. So that flow of electrons, and there's always lots of them, this is basically what current is. So again, the flow of electron, the free flow of electron is always going in one direction, kind of like your blood in your arteries and your veins, and it's always in one direction. There's no backflow, at least in a normally functioning system. So the flow of electron creates a charge. So this electron flow, I'm going to summarize it here. Electron flow results in a charge. Now, in your previous unit, you learned about charge. Charge is measured in coulombs, as you recall. And this charge, it has a symbol Q. And when you measure the charge flowing over time, this is what current is, and it has a symbol I. So current can be defined as the amount of charge that crosses a surface per unit of time, much the same sense that a river current is the amount of water flowing per unit of time. So how you would define a current, the current of the Red River, for example, is basically the same definition as a current, which instead of water flowing, it is electrons flowing in a conductor. So the definition is current is charge flowing over time, or delta T. Now, what is the unit of current? Well, the unit for charge is Q, and the unit for time, as you know, is seconds. So this is Q is coulomb. So I wrote down the symbol for charge there. So this is coulomb per second. And a coulomb per second is exactly the same as a big A. And this stands for ampere. A quick history, Andre Ampere was the first person who first described what is a current. So it was named after him. So coulomb per second is ampere, and this is the unit for electrical current. So now that we have an equation, let's take a look at some examples. So our example 1, you have 20 coulomb of charge flows in a time of 2 seconds. Calculate the current. Okay, so you can then look at what is this unit C. C is coulomb, which is charge, and seconds, that gives you the time. That's the time elapsed. So we're looking at calculating the current, which is I. So again, we need to remember that current, really the formula is the definition, as you recall. And the equations are just a description of what they are, what the concepts mean. So current is charge flowing over time. So we're looking for current. So the charge is 20 coulombs divided by a time of 2 seconds. So you have 20 divided by 2, and that gives you 10 amps or 10 amperes. You can just shorten it as amps. Okay, example 2. How long does it take? So now we're looking at time. How long does it take for a current of 0.15 amps to transfer a charge? So you have the Q and you have the I. We're looking for T. We have 2 questions here. You're also looking for the number of electrons. Okay, so we look at current is charge over time, and we're looking for Q. Q is it. There you go. So the time is what we're looking for, actually, not the charge. So T is equal to Q over I. So the Q is 16 coulombs divided by 0.15 amps. And do that on the calculator. You have 160 seconds. That's the first part of the question. And then we're looking at how many electrons are transferred during this time. Well, at this point, I'm going to define the charge. And recall, neutrons do not have any charges. It's neutral. So we call this elementary particle. One elementary particle charge, which is, it's either a proton or an electron. In this case, you're looking for how many electrons, and the charge is 1.6 times 10 to the negative 19 coulombs. So for every single electron, that's how many coulomb it carries. So now we need to, this becomes a unit conversion, because you have 16 coulombs here. That is the charge of this, this much current. So we're now looking at how many electrons actually get to move to create that charge. So it's just a unit conversion. So we're going to start with how many charge do we have? It is 16 coulombs, and I need to get rid of the unit coulombs. So I'm going to put 1 electron as a charge of 1.6 times 10 to the negative 19 coulombs. And as you can see, the units will cancel each other, and that will give you 1 times 10 to the 20th electron. And that is a lot of electron to create such a relatively small charge. You do need to remember that electrons are very, very small. Okay, example 3, we have how much charge is transferred. So now we're looking at Q. So we're looking at Q by a current of 1.3 amps in 0.25 hours. How many electrons are transferred during this time? So we're looking at Q is current times the time. So we have I of 1.3 amps, and the time is 15 minutes, 0.25 hours. Now this is in hours. So again, we need to convert this into seconds. So there are 60 minutes in 1 hour, and so that goes, and then there are 60 seconds in 1 minute. So again, we're doing unit conversions, and that is going to give you 0.325 coulombs of charge. So looking at how many electrons need to move to create this charge, so we go 0.325 coulombs times 1 electron has a charge of 1.6 times 10 to the negative 19 coulombs. There you go. And you get 2.03 times 10 to the 18 electron. Now remember, you're actually counting how many electrons. So this is a number. It's not just how much, it's how many electrons. If you look at your number, it says 2.03. You have to remember this is to the power of 18. So this is actually a whole number. It's 2.03 followed by 18 zeros. So after the decimal there. So it is a lot of electrons again. So we know now that electrons move through metal wires. We call that conductors. Negatively charged electrons leave the negative terminal of a battery. That makes sense because they are negatively charged. So the pressure would be higher in the negative terminal of the battery. So let's say you have your positive terminal here and you have the negative terminal there. And let's just make so that's your battery. And let's just put something here. Let's say you have a light bulb there. So your electrons come out of the negative terminal. So this is where the electrons come from. And this is where they live. As you can see, there's negative charge here. That's because that's where the electrons are. So there's a higher concentration of negative charges here, and that is where they get pushed out. So the electrons go from negative to positive. However, it is customary not to use the flow of electrons. So when we talk about electric circuitry, we use the what we call conventional current flow. And conventional current is moving from the positive terminal of the EMF. So this is where your conventional current's coming from, and it's going to go back to the negative terminal of the EMF. So we trace the conventional current flow and not the electron flow. And this was, again, for reasons that date back to the time when it was believed, they used to actually believe that it was the positive charges that moved through the metal wire. We now know that it's the electrons that move through the conductor, causing current, and that is coming from the negative to the positive. But conventional current is the hypothetical flow of positive charge that would have the same effect in the circuit as the movement of negative charges that actually does occur. And so we don't change the convention. I also want to think of it another way, though, is that if you're swimming, and let's say you want to go this way. Let's say you want to go here. That's your body. This is your body. You want to go swim this way. You want to go swim there. There's the arrow. If you want to go swim there, let's call this the electron. Let's say you are the electron because this is matter, right? Let's say this is matter. Everything is about matter and energy. If you recall, I said this on the very first day. So let's say you are the electron and the electron wants to swim here. So this is the arrow. You want to go swim there. You're in water. You want to swim. How do you suppose you get there? What do you have to do to the water? Well, you have to push the water backwards, right? So you push the water here. So if you want to swim there, you push the water here. So in this direction. So you could imagine that this is the current. You actually have to create a current to push your body in that direction. So This is the energy equivalent. So you have this energy, which is current. So essentially, current is the effect of the electron flow. So we just have to remember that current flows from the positive to negative, even though electrons come from the negative to the positive. But it doesn't matter because the effects would have been the same. So they just didn't change the convention. Okay, so let's summarize here. Electrons flow from negative to positive, while current or conventional current, should write down, conventional current flows from positive to negative. And this is what we focus on when we look at the electric circuitry. We look at the current, not the electron flow. Number of electrons and energy gain. So from the previous unit that you just finished, recall that the charge on an electron is this. We just said that in the previous page. So that is, again, I'm going to rewrite this here. This is called an elementary particle charge or elementary charge, because this is the charge for a proton. So the proton is just positive 1.6 times 10 to the negative 19 coulomb, and the electron is just the negative number. So it's the same thing. Protons and electrons have the same charge, but they do have different masses. Protons are a lot heavier than electrons. So this value can be used to determine the number of electrons that flow in a circuit in a given time. We did this previously in the previous page. So Q equals current times time. If the unit of current is amps and the unit of time is seconds, and the charge is in coulombs. We already just did that. So just reiterating the facts. So for 20 coulombs of charge, the number of electrons then is, we could also find then the number of protons. But we're looking again at the number of electrons in this case. So you have 20 coulombs. So we need to cancel the unit coulombs. So we look at a charge of 1 electron is 1.6 times 10 to the negative 19 coulomb. As you can see, the coulombs then gather out, and calculating this, that gives you 1.25 times 10 to the 20th electron. And again, that is a lot of electrons that you need to create a 20 coulomb charge. So again, from earlier lessons here, we learned that the amount of energy gained, and we're looking at energy now, by an electric charge as it passes through a potential difference is given by, I don't like the way it's written here, it's potential energy. Big E is always energy, and the subscript is the type of energy that we're talking about. So the change in potential energy is equal to charge times the change in voltage. So that's the potential energy. I believe you were using that in the previous unit. So in 20 coulombs of charge, if 20 coulombs of charge flows through a potential difference of 12 volts, then the energy gained by the electron is, again, this is potential energy. You got your 20 coulombs of charge and 12 volts of potential difference, and you're going to get 240 joules of potential energy. That potential energy is going to create or lead into potential difference, and that's that led to the potential difference of 12 volts. So we have some questions here that you can do to practice. So I'm going to leave this for you to do, and I'm actually going to assign these questions. So I shouldn't have put quiz there. I don't know why I put quiz. I guess we could call this, I was going to say take-home quiz. Just call it practice assignment. Numbers 1 to 4. So try that one. I'm actually just going to jump to number 4 here and just take a look here. So you have in a nerve cell, 1,000 sodium ions may flow across a membrane in 4 milliseconds. Again, recall this. That's the time is 4 milli, as you remember, is 10 to the negative 6 seconds. So we always have to convert all our units to SI or metric units. So you have to convert that to seconds. The charge on the sodium ion is the same as the charge on an electron, but positive. So we know the charge is 1.6 times 10 to the negative 19 coulombs. But if you take a look at the question here, it says in a nerve cell, you have 1,000 sodium ions. So that means that to create that, you have to have 1,000 electrons taken away from the sodium to make it a positive charge. So just a quick review here. So you have this sodium. Remember, it has 11 electrons, 11 protons. So if you were to look at a membrane in a nerve cell, you actually have 1,000 of these sodium ions. So we're going to have to find a way to incorporate that number 1,000 into the charge. So I'm going to leave that to you. Just want to make sure that you use that. So this is, again, remember, is the charge of 1 electron. Well, you're dealing with 1,000 sodium ions. So again, I'm going to leave these questions to you for an assignment. And if you can just answer these on a piece of paper or directly on the book, scan or take a picture of these and email them to me, that would be great.